It's my great pleasure to introduce Professor Stephen Boyd, who is the Samsung Professor of Engineering at Stanford University. I actually met Stephen back in 2002, when he was giving the plenary at CDC, which is the Controls Conference. I really remember him saying how in control, linear things are easy and nonlinear things are hard, but in optimization, convex is easy and non-convex is hard. Certainly, his career, he has had a tremendous impact in optimization, and without any doubt, he's one of the world leaders in that area. He's written 3 books in linear control, linear matrix inequalities, and convex optimization. He has received way too many awards to be named, but including one of the top awards in control, the ONR Young Investigator Award, IEEE Fellow. But most importantly, he was elected to the National Academy of Engineering in 2014. It's really a great honor to have him here, and welcome to ICCV 15.
Great. Thanks. Thank you, Renee. And I think I'm not going to use this. I'll use the lapel mic. We're all ready to go. So first of all, thank you very much for inviting me. I was going to say I have never been to a vision conference before, but it's a lie. I did go to one a few years ago. So anyway, I'm happy to be here. What I've seen so far has been really, really cool. So I guess keep it up for tomorrow. So what I'm going to talk about today is convex optimization with abstract linear operators. And this is joint work with a PhD student of mine, Stephen Diamond, who's here somewhere, maybe, I don't know, there he is, he's over there. So, and I guess you all know what joint work means, right? So just, do I have to spell it out? You're not going to make me, okay, fine, we don't have to say that, okay. So, I'll start with, I know that some people here know a lot about convex optimization. I know others know much less, and so I'll give you a very quick overview of that. And you might be asking, like, what does this have to do with vision? I mean, you could ask that. Actually, if you already came in here, it's too late or something, so you can't. I guess if you're at the back, you can leave. But it actually will have something to vision, or there'll be a hint. So, okay. So what I'm going to do is, first, I'm going to look at, I mean, this is a bit strange. This is interesting. I don't know what this is. I can't see it, but that's okay. So I'll be able to point to maybe this slide and this one. And I could try that, but there's some serious like angle control issue there. Those are like, you know, milliradians right there. But okay, that I can actually hit. So, okay. All right, but I don't want to give people whiplash. So, okay. So I'm going to start by talking just about, you know, what's convex optimization. It'll be quite brief. At the high level, I'll say, you know, what is it and why should you care? We'll look at some examples, and in fact, oh, hey, now we know what the screen is. Look at that. Okay. I'll look at some examples, and in fact, they are, you'll see, they're baby image processing examples, a few of them, and maybe one that's not. Then the real topic of the talk is on matrix-free methods, right? So how do you make these generic methods, how do you bring them to problems with millions of variables, the kinds you might encounter, for example, in vision, right? So, and then I'll just wrap up, and that'll be it. So, okay. So I'll start with convex optimization, and that's an optimization problem. Looks like this. You have a variable that you have to choose, that's x. These are the traditional symbols, right? So you have to choose a variable, and you're judged by an objective. So you want to minimize, you could just as well maximize something, but you minimize an objective function f0. Could be anything. You have equality constraints. They have to be linear. We'll talk about some of that a bit later. And there are inequality constraints, and by convention, these are written as a function less than or equal to 0. And there's one more catch. To make this a convex problem, all of these functions, f0 and all fi, they have to have positive curvature. They have to curve upwards. That's what this just says, that they have non-negative curvature, right? And so this is the asymmetry that Renee was referring to, right? That, you know, you might think something's easy if it's linear, or non-linear would make it hard. And in fact, in optimization, that's wrong. The correct view is actually weird, and it's not obvious, and it's this. It's that curvature doesn't make it hard. Negative curvature makes it hard, right? So that's actually what's not obvious. Okay. Now, what's emerged as kind of a very standard form, and it looks super specialized. I mean, it's called cone form, and it looks like this. It's also called a conic program, and it looks like this. You minimize a linear function subject to, there are your equality constraints, but all the nonlinearity, everything in the objective and all the constraints, that got pushed into one constraint that simply says x is in a cone. Now, if that cone is the non-negative orthant, variables with non-negative entries, this is a linear program. I mean, it's something that would be familiar to people in, let's say, 1950. But if you swap out k and put in something else, like something involving a Euclidean norm, it's something new and different. If k is the positive semi-definite matrix, this is a semi-definite program, right? And so this has emerged as essentially the modern canonical form. If you learn a bunch about convex optimization, you spend weeks transforming various practical problems to this by hand. In fact, what I'm going to tell you about is how a lot of this can be done in an automated way. So this is, the cool thing about this is if you're interested in the theory or whatever, of course you need to know about it. The great part is this is essentially, this is the modern canonical form. It's the intermediate form for convex optimization. It's like 3-byte code or something like that will see you compile a problem written in a high-level language to this, and then this is what's solved. By the way, the consequence of that is not that many people need to know about this. So, okay. So why should you learn about convex optimization? Well, I'll just give you a list. Oh dear, sorry about that. I'll just give you a list. The first is, I mean, there is a beautiful theory of it. I mean, the mathematics is 100 years old, right? So, and it's absolutely beautiful mathematics, so it's interesting. I mean, and some of it, by the way, is actually practical, right? In the sense that, for example, duality says that there's a very organized way to generate lower bounds for problems, right? And that's extremely useful in practice. So it's not simply that it's beautiful theory, it's actually also occasionally useful. There we go. Okay. Much more important than that is that there are effective methods that you can solve. So you can solve these problems, basically. It's a strongest form of solve. It doesn't mean you did something and it worked or it's good enough in practice. There's nothing wrong with either of those two. But in this case, you don't have to make any apologies. You typically just get the solution, a solution, I should say, if there's multiple. And if you care about the theory of it, then, they're polynomial complexity. Okay. A very nice thing is that it unifies a whole bunch of different things, right? You get this great intellectual economy, right? You learn about one basically small area of mathematics, and now all of a sudden you can do stuff across many, many different fields, right? So the machine learning course at Stanford, or anywhere else, the first, 5 weeks would sound kind of disjointed. You say, oh, we're going to do regression, and then now we're going to do lasso, and now we're going to do support vector machine and logistic regression and blah, blah. And they all look different and sound different and all that kind of stuff. And it turns out it's way easier, which is indeed the way it's done now, is to say they are all convex. They and a lot of others are all convex, right? So, and it's just easier. Even if that has no effect on how you solve the problems, this is interesting. It's a nice way to organize things. It's okay. But the main thing is this. There's just tons of applications, right? So this is the part that I find kind of compelling. So, okay, so the application areas are areas like machine learning and statistics that comes up all the time. Finance, tons of problems there. You could even argue that some of the most basic concepts in finance, like arbitrage-free, essentially it's directly from convex optimization. Areas like supply chain, revenue management, advertising, control, lots of problems. Signal limited processing, even vision. And I know that because I just went through some posters and saw at least a couple. So networking, circuit design, all sorts of crazy stuff. You get into mechanical structure design. So designing light but strong mechanical structures for aerospace applications. It is now done, a lot of it is done using convex optimization methods. Okay, so let me tell you a little bit how you solve these problems. And then this is the preamble to what this talk is about. So medium scale solvers, if you've got thousands of variables and constraints, or maybe tens of thousands in the right structure, maybe 100,000, but you're really lucky or whatever with the sparsity patterns, then these things are just reliably solved now on a single machine. I mean, my laptop is more than enough, right? But if you get a bigger machine, like with, 32 cores and a bunch of memory, you can solve quite large problems, and it's completely reliably. So these exploit problem sparsity. And by the way, one of the themes, one of the things I want to talk about is this, is what's actually changed, and one of the reasons it's had a bunch of impact in some fields, else not vision, I might add yet, is that it's actually completely reliable. There's no tweaking of parameters. There's no like, oh, you know, you should try this method. Oh, how about that? Oh, you should turn this regularization parameter down. Oh, you should use this method. None of that. They just work, period, right? Now, by the way, that's pretty much only in fields where the number of variables, and actually when I often give this talk here, it's too late for all of you, I should add. But I will usually tell people, I say, look, if you're young and thinking about going into a field, just by the way, if you went into a field where that was like the typical number of variables, you could just use the methods I'm about to show. So you already made the mistake of going into a field with much larger problems. So, okay, sorry. Well, actually, there's going to be a hopeful note. You'll see. Okay. So I already said this. You know, basically, there's no for these size problems, there is no algorithm tuning, no babysitting. This is extremely important. If you're going to do, for example, embedded control, you know, your problems are going to be coming at you 100 times a second, and here's how many you have to solve. 100%, always, period, end of story. So you cannot be sitting there tweaking parameters or something like that, or say, oh, it didn't converge. You can't do that. Okay. So it's not quite a technology, but it's getting there, right? By the way, when I tell this to people who work on convex optimization, they get absolutely insanely angry, and they say, well, you're just telling people to use it like a black box. And I say, exactly. And they're like, but they don't know what's inside. I said, oh, that's exactly the point. And anyway, so it's fine. But then I say, look, that's actually the highest praise. The highest praise is that what you do is technology, because it means, it doesn't mean there's no theory. It means there's lots of theory, but you figured it out. You figured out the algorithms, and you have flawless implementations. So good that other people can use them, period. That's technology, and it's super good. It's great. It's the highest compliment there is. Okay. And it's used in lots of areas. Okay. Now let's get to large-scale solvers. This is what people here would usually be doing. So you might have 100,000 to 1 billion variables and constraints or something like that. And so here, usually this is done by custom methods, and it's done on a problem-by-problem basis, right? So, and you know, you could go to, you go to NIPS and find out what the current coolest method is, and you use that or something like that. Or you ask, you could use like, mirror descent with Nesterov acceleration, or some of you probably know what I'm talking about. So you use a fashionable method, right? Now, also, there's disadvantages of this is you have to do it for each problem. One advantage is you can actually exploit fast transforms, like Fourier transforms, convolution, things like this. And so in areas like medical imaging, and I should mention ordinary vision, when you have convolution or something like that, you have fast operators, you should be exploiting that. And so the downside, the good side is you're solving gigantic problems. The bad side is this is going to require custom implementation, and you're going to have to tune each problem, right? On the other hand, you walk up to someone who's just tuned, a regression, a logistic regression solver that handles 1 billion variables. By the way, many of these are in production right now. You can guess where they are, but many of them. And, I'd say, but you custom tuned it. And they'd say, yeah, but I'm solving 1 billion variable regression problems in production. I think that's fine, right? So anyway, so it's okay. Okay, now I'm going to tell you something that maybe many of you here don't know about, because this has mostly been used so far in areas where the number of variables is modest, like 10,000 or something like that. And it's high-level languages. So the idea is this. You have high-level language support for optimization, right? So it's convex optimization. You describe it in a high-level language. What will happen is that description is automatically compiled or transformed to one of those cone problems. That's the intermediate form. And then that cone problem is then solved by a completely generic solver with 0 babysitting and 0 tuning. This is the idea, okay? So this is the idea, and it would look something like this. We'll see some snippets shortly, but this is the idea. You write your problem up here. That's essentially a program. This is compiled into one of these forms. That's a canonical form, so this is called canonicalization. Now you take any solver for this form, and you get an answer. Here's X or whatever. And then you unpack from X. Part of the canonicalization is that you have a mapping that will tell you how to recover the original variables from this, the variable here, right? So this is the picture. It's not complicated. And there's a bunch of implementations of this. So implementations, I mean, actually it has a long history. People writing languages for solvers goes back to the 70s. But those were completely general, and they had no support for convexity and all that kind of stuff. I think they recognized if a problem was a linear program, and that was it, okay? More recent ones, and they're not even that recent, maybe, well, 10 years ago or less, would be something called YALMIP and CVX in MATLAB. And maybe a few people here know about CVX in MATLAB, but probably not for an image problem because they're too big. So a more recent one is CVX Pi. That was actually written by Stephen Diamond when he was an undergrad. So that's in Python, so it's actually finally, we have these things in real languages. And then there's a Julia implementation, which is called convex.jl. And for medium scale problems, that means 10,000 variables, these are actually now very widely used. So here's what they look like. Here's a snippet of CVX. And so the idea is, well, we can even figure out what the problem is. It says this declares a variable that says that x is now a variable object. Its dimension is n. And then you simply say minimize, and that's an expression. And the expression is parsed, and then it has to follow certain rules so that we know for sure it's convex. Okay? But nevertheless, it's a lot of things. Once you learn a very short rule book, and you'll know how to do this. And then you simply say subject to, and then that's a constraint, right? And it doesn't have exactly the form I showed, but what you do is you subtract 1 from both sides, and this would say the infinity norm of x minus 1 is less than 0, and it would know that's a convex function. So this is the idea here, that you'd type this in, exactly that, and you'd execute that. And what would happen is, during execution, the problem would be converted to a cone form, and then it would be solved. You'd have a couple of solvers because, 1 in 10,000 times one of the solvers will fail. And sometimes you just might want to get 2 opinions, right? So, by the way, they almost always agree, but just in case. And that's the idea. And then when this terminates, this thing which in this scope is an object, right? It's a variable object. At the end, it's overwritten with an array, a double array, which is the solution, okay? CVX Pi, this is in Python. And so again, here's just a short snippet so you see what it looks like. The details aren't important. Actually, what is important is that it's unbelievably readable, right? So that basically the code you write is essentially the mathematics. You say what you want. So here, you declare a variable object. You form a cost. That's an expression. That's an object, which is a convex expression. And then you form a problem, which consists, that's the constructor for a problem, and it says it takes an objective, and it takes a list of constraints. In this case, there's only one element in the list, which is a constraint. So here, this less than or equal to, this is, the relop is actually, this is overloaded to take, an expression, relop expression, and it returns a constraint object, right? So it's all pretty clear. This forms the problem, you haven't solved it, and then if you call the solve method on the problem, that will have a side effect of, in fact, writing on the value attribute of all variables, okay? So, I mean, this is very clear. This is the idea, right? And so the idea is that in use, you do stuff like this, right? You do not sit around, implementing like a gradient method or something like that, where it's your problem to deal with the stopping criterion. You don't. It's all embedded in here. Okay. So these types of languages, right, have done things like this. First of all, they enable rapid prototyping for small and medium problems, not large-scale problems, because they just don't work, period, right now. That's part of the talk, actually. They just don't work. For small and medium, it means you can prototype stuff. I mean, it'll be weird. I'll be sitting in a talk somewhere, not here, well, it wouldn't work here, but other place, someone will be talking, and I'll actually type in a convex problem while I'm sitting in the back of the talk or whatever, and then I'll come up. It's actually kind of annoying. I'm annoying, because then the person will say, I'd say, that's convex. I'd say, oh, no, it's not. And I'd say, no, it is. And they'd say, oh, no, absolutely. And I'd say, well, let me put it another way. I coded it, and here it is, it's running, right? So just because it's so easy, you just type in 5 lines. Okay. For teaching, it's a complete game changer. A total game changer. It turns out, if you look at the classical optimization course goes, here's the gradient method. Here is, quasi-Newton method. Here's the Newton method. Here's the, this method. Here's that method. And then the quarter semester finishes and you're like, it was a big pain in the ass and why did you take that class? And then the result is no one takes classes like that anymore. Everyone kind of agree? Okay. So This is totally different. I mean, when what you do in class is you write stuff like this, and basically, I mean, yes, do they use the gradient method? Yes, once, exactly once in the class, right? It's the same way, should everyone write an assembly language program, right? And the only correct answers to that is students should write an assembly language program either 0 times or once. Oh, except for the 0.02% of people who it's in our interest go into compilers, right? We need those people, and they should write a lot of them. Actually, they shouldn't write any. They should write the back end that generates the code, but that's another story, right? So this is the same thing. You should not be mucking around at this gradient level and stuff like this. I mean, it's kind of, now, by the way, this is if you have less than 10,000 variables, so just, you're exempted. Okay, so. Anyway, what it does in teaching is unbelievable because you can have a course and you can do finance, you can do small vision problems, you can do control, you can do signal processing, you can do statistics, machine learning, all sorts of stuff, networking, and actually just do it, writing, 5-line scripts and understanding everything. Okay, you might ask how much slower is this, and the answer is it's slower, of course, I mean, we can hope, right? We can guess that, but actually, what's weird is it's often not much for these smaller problems. It's often like quite modest, right? It's maybe 10x slower than a custom implementation, right? So, if you're going to put something in production and you really care about speed, then okay, fine, don't use this, right? But for rapid prototyping, it's unbelievable, right? So this is the idea. So this talk is actually just about this, because now that was all preamble, and now the talk is going to start. So it's about this. It's basically, how do we make CVX-Pi work for large problems and fast operators? That's what it's about, right? So, by the way, if you want me to translate that into vision, it's something like this. How do we make something like CVX-Pi, or indeed CVX-Pi, work for vision scale problems? That's it. So, there's actually some, progress on that. But before we go on, I'm just going to do a couple of examples. By the way, the examples are actually, 2 of them are vision, 1 is not. They're very old, but it's just to give you the flavor of what this looks like. So, okay. So we're going to do image in painting. I mean, I can go super fast here because everyone gets that, right? By the way, there's a gazillion ways. If I was going to do if I was going to do in painting, I would do it totally different ways. But this is like if your coding time was limited to 30 seconds, this might be a good choice. Okay, so here it is. What it is you're given, you want to fill in the pixel values in the obscured or corrupted parts of the image, which you know. And then what you do, something very, very simple, and this is from 1992, so I guess I can say most of you were born by then. Yeah. Okay, what? Come on. You really weren't? No. That's ridiculous. Okay. You're students. Fine. Anyway, so then it's embarrassingly simple, right? So you simply minimize the total variation. Let's note a couple of things. How many other images do you need to train this sophisticated method that was developed before many of you were born? Not many, okay, some, right? How much data do you need? 0. You'd say, let's see, what else is it? Well, what do you need to tune? Oh, nothing, right? So this is amazingly simple. It just says, and this is very important, that's the total variation. That's the gradient of the image. That's a 6 vector. Very important is that there's not a square there, because then that would be Laplacian, and you'd get a smooth image. This is an L1 norm of the gradient, not an L1 norm because it's really a norm of a 6 vector, right? So it's a sum of norms norm or whatever you want to call it. It's a completely elementary convex approx. And actually, embarrassingly, even though this is like embarrassingly simple, uses no data of any kind. It's not a bad prior for images, right? I mean, it's a level 0 prior. So this is how you do this in CVX-Pi. And the point is, by the way, obviously, this has been done since the 90s, okay? So it's not like there's some big deal here. How would people do it now? You might make a grad student go write a bunch of C++ and do this in write some ADMM method, or I don't know, they would do something like that. That's what would happen. But actually, this is how you would do this in CVX-Pi. You would simply declare 3 variables. These are matrices, R, G, and B. You'd stack them into a giant variable X, and you would simply write that. It is exquisitely readable, okay? Now, how much slower will it be than some custom thing? This, I mean, at the moment it might be 100x slower, but actually with the stuff I'm going to talk about, this might end up being 10x slower. However, the coding time would have been 1,000 times faster, right? Maybe a lot more, right? So this is the idea. So that's it. You simply call the solve method here, and you do it. Now, by the way, the advantage of this, we'll take a look at how this works, right? So, I mean, here's Lena, our you know, I figure I'm in a vision place, so we'll show Lena, right? And here are some corrupted, here are some pixel values that you don't know. And it's not like this is that hard to do. But again, this is that five-line program. You minimize, it's from 1992, the proposed method. 5 lines in Python. And this is what you get. Now, could the methods I've seen here, actually, I could do better instantly if you, instead of 5 lines, you gave me 50. I could do a lot better. What's shocking here, just for those of you, this is not state of the art, is actually how good it is for a method that's like really incredibly stupid. It's from 1992, uses nothing, no prior images, right? You can code it in 5 lines of Python and call the solve method, and you actually get something that's pretty good. So, okay. So another example with most of the pixels removed, and you get something like that. And there's artifacts you can poke around. But again, for a 5-line program, I think it's actually not so bad, right, is the idea. And of course, the point is not that you would do this. The point is now, if you looked up and said, oh, I've got a great idea, I'm going to add this constraint, or I'm going to add this term to the objective, or I'm going to add this, or I have a prior, or blah, blah, blah. Any of those things now takes you about 14 seconds to add and try, is the point. That's the idea, right? So that's how this has accelerated research in other areas. Okay, we'll look at another quick one, is colorization. So in colorization, you're given some black and white pixel values and a few colored pixels, and the idea is from that, you're going to impute or guess the color values everywhere. They have to agree with the black and white values, and again, this is not quite as old, but these are not new ideas exactly, right? And again, the code is very, very short. It looks like that. So the coding time here might be, I don't know, a couple of minutes, maybe less, right? That's as opposed to, if you told a grad student, go deal with this, it might take them a week or 2 or more, depending on how snappy they are with modern large-scale optimization stuff. So you just write this. It's completely readable, 100% readable. And then you might get something like this. Here's your original image, and here's the black and white version of it. And then what we do is we just take 2% of the pixels, and then there's the color reproduction. And it's by no means perfect, but it's actually like shockingly good, right? That means that basically 1 in 50 pixels, we give you the color, right? And then from there, you're extrapolating, I guess, 50 to 1, something like that, right? So it's actually not bad. And by the way, this is with nothing. Could you do better? Of course you could do better. If you had a lot of data and you had other stuff or whatever, of course you could do a lot better than this. The idea is, what's shocking here is how well you can do with so little. Okay, this is what happens if you're down to 1 in 1,000 pixels, right? So that means basically in a typical 30 by 30 patch, you will be given 1 color sample. That's it. And it's fine. Okay. The last one I'm going to talk about is not from imaging, it's non-negative deconvolution. I'm going to talk about it because it's going to come up in the next part of the talk. So non-negative deconvolution, again, it's an older problem, but it looks like this. You minimize the norm, or norm squared, either same thing, of a convolution. So you have, that's some convolution kernel C, convolved with X, minus and then some right-hand side B. And this is subject to X being non-negative, and this comes up all the time. I mean, in 2D, by the way, it comes up in some image or astronomy, things like that. But it also comes up, I mean, in 1D cases as well. Actually, deconvolving like spectra, right? So if you have, if X is actually a density, and this is atomic number, and you have a piece of equipment with a diffusion, I mean, then you'll get something like this. Okay, again, this is that's an old problem. I could go to Google, I could type, source code, non-negative deconvolution. I'll find something pretty quick, right? That's not the point here. I'll say a little bit more about that a bit later. Here, what you do is that's the code. It's just completely readable, right? I mean, that is the point. Is that the source code looks like the mathematics. That's the point, right? By the way, the real point here would be something like this. we'll end up with something here that's maybe 80, 100 times slower than if I made a grad student write me a custom version for this, okay? That's what's going to happen here. And by the way, that gap is going to close over the next couple of years, right? The difference, though, is what if you came along and said, oh, but you know what? I have also some known linear equalities on X. Like I have 10 of them. You know, you can make up all sorts of problems with it. Like, you know, I don't know, you know, whatever. You know some linear functions of X, right? Then the point is that the custom code that was written before and took like one grad student week doesn't work anymore, right? And so it's going to take another grad student week minimum to adapt it. By the way, what will typically happen is you'll make the grad student do this for a week. They'll come back a week later and they'll say, great, that's fantastic. You know, how did it go? Is it getting better results? And they'll say, no. At which point you say, oh, well, sorry. That's research. So anyway, so fine. So here's an example. So here's the true X. It's sparse, right? So that's the true X. Maybe that's a spectrum of some sort, right? And then what you get is a convolution with what is obviously a pretty big Gaussian kernel, right? So you get and so what you see with noise, so this is what you see, is the green thing. And now you want a method that's going to, you know, find these things, right? Well, this is, first of all, it doesn't even look like you could do it. It's ridiculous, right? I mean, you see a bump here and you'd say, well, okay, there's a bump there. Obviously there's something there. And there's a bump here and there's obviously something there. Visually, I would have gone for 2. Okay? I mean, you know, that's what I think anybody reasonable would say that, right? There's no one who could look at that and say, oh, you see how this is a little bit flatter here. I'm going to add one here. This is ridiculous, okay? So, in fact, this looks like a hard enough problem that you just simply can't solve it, right? So this is what happens when you solve that one convex problem. The true is the blue and the red is the recovered, okay? So, I mean, this is, of course, the basis of compressed sensing and these kinds of things, right? It's very impressive. Actually, if you don't, like once a week, sit down at a quiet place, you know, breathe steadily or something, and sit down and actually just reflect on how amazing this is, then you're not getting what it's doing, right? This is like ridiculous, right? But this is sort of standard, this is compressed sensing. This is how compressed sensing works, right? But it's pretty weird. And of course, it didn't get it exactly right. You can see that it's off a little bit here, but it got the number of sources right, awfully close, got the amplitudes right. It's pretty spooky. So, by the way, if you're not impressed with this, then you haven't fully thought about what you're being shown right now. This is unbelievably impressive. I mean, look, it's part of, I mean, you know, I don't know, the students in my class, they do things like this and for homework, and I'd say, well, what'd you think of problem 3? And they're like, yeah, that's cool. And I'm like, what's wrong with you? And they'd say, it's convex optimization. I'm like, that's not the right, yeah, of course it is. But like, that's amazing. Don't you realize that's amazing? They're like, yeah, whatever. So it's kind of like, every now and then you need to sit down and be mindful about these things, right? Oh, by the way, this is no different from the others. Could you do better here if you used more information? Like, what if I told you ahead of time that source is sparse? The answer is, of course you could. We have iterative methods that would do this, you know, like that. You might even be able to use, are you ready for this? Deep learning. We'll get back to that. We're going to get back to that. Don't worry. But let the record show that it took me this long to get to that. Okay, we'll get back to that. Okay, matrix-free methods. Okay, so now it's going to be a whirlwind tour of matrix-free methods. Let's see how they work. Well, the idea is old. This basically is the foundation of scientific computing, like all of scientific computing. So it's not like this is a new idea. So here it is. You know, you have a linear function. Of course, you can represent as matrix vector multiplication. I mean, duh. So, but the idea is you don't form, store, or use the matrix A. Okay? So instead, you're going to represent it as and there's going to be it's going to be an abstract entity, and it's going to be a forward adjoint oracle. Again, these are, you know, fairly standard terms. I mean, not terms, sorry, ideas. The terms are you know, we made up, but anyway. I mean, so the idea is you're only going to access that operator through the forward operator. That means you'll give it X and it will return AX. Or you'll give it Y and it'll return the adjoint, which is A transpose Y. Okay? And now obviously you can wrap a forward adjoint oracle around an ordinary matrix, right? You just, here, ready, I'll do it right now. Ready? Return A times X, right? And here's the adjoint implementation, return A transpose times X, or times Y, sorry. There, but the idea is we're interested in cases where you can do this much more efficiently than that, both in storage and also in computation, right? And this is the key to scaling to large problems, right? So there's lots of examples. I mean, people know these things, right? I mean, they all come down to the DFT, the discrete Fourier transform, which is computed by the algorithm, which is the FFT. Okay, so, and from that you can build fast convolution. So you can write convolution with a kernel, which is normally like, n squared, and now it's n log n. There's tons of these, right? All these fast transforms like there's Gauss transform, all the wavelet transforms and other things like that. Those are typically O of n, but with a pretty healthy constant in front, but still. Okay. Other ones would be things like Lyapunov and Sylvester mappings. That's a matrix, and it's return. What you do is you get the matrix which is multiplied on the left and right? And this would be O of n to the 1.5. Sparse matrix multiply would be another one. A non-obvious one is if you have a sparse triangular matrix, the inverse generally, by the way, is quite dense, right? But we can multiply by the inverse by using back substitution, right? And the adjoint would be upper triangular, and so we use forward substitution, right? So there's a bunch of examples of these things, right? Okay. Now the idea is you can actually compose these. I mean, what you do is you represent a linear function as a graph, as a computation graph. And you start with x on one side, you go through these things. Each of the edges is going to, each of the nodes is going to store one of these operators, and the edges are going to be partial results, right? And so to evaluate f, you simply walk the graph and evaluate. You call the forward function. And by the way, to evaluate the dual, the adjoint is automatic. You simply walk the graph in reverse direction, and you call the adjoint operator, okay? So here's an example. I mean, I got 3 fast operators, C, B, and D. And so here's the mapping, A, which I blocked into 2 vectors. And so that would have a computation graph like this, right? And so this was it. This is the idea. Copy is simply, it's a stupid operator. It takes its argument and produces 2 copies of it and spews them out, okay? By the way, the adjoint of this, we just transpose A. We reverse the computation graph. The adjoint of plus is copy, and the adjoint of copy is plus, right? These are that's literally the adjoint operator. And so here's the adjoint graph, okay? So, and now you can imagine all sorts of methods where, if you had multiple processors and a bigger graph, you could do things like assign processors. You could have a pool of processors, and when one comes up and is ready for another one, you assign them one of the ready to compute. You have a ready list and that sort of stuff. You can imagine fancy stuff. Okay. So these tie in with matrix-free methods. So that is a standard term. So the idea of matrix-free algorithm is this. It's basically, it does something, like computes something where there's a matrix involved, but you never form the matrix. Your only interface to that matrix is through this, through actually multiplying by A and multiplying by A transpose. That's the idea. There's nothing more. That's the idea. Okay. The good news is there's lots of matrix-free algorithms, and the oldest and most widely used is just conjugate gradient. So conjugate gradient algorithm is in fact a way to solve a least squares problem, and each iteration involves only mapping from X to AX and Y to A transpose Y, right? Actually, it does it exactly in theory in n steps. In practice, it's got terrible round-off issues, and so it doesn't work in any way. The real advantage of things like CG is not that you can solve a 10 million variable linear system in 10 million steps, which you can't anyway in practice. The really cool part about it is the way you really use CG is this, is I can get a very good approximate solution of a 10 million variable set of equations in, let's say, 2,000 steps. That's actually extraordinary, again, if you stop to think about what that means. It's unbelievable. It means you solved a 10 million by 10 million set of linear equations, okay, not solved, but pretty good. And you did it only 2,000 times doing forward matrix multiplication and adjoint. That's actually pretty impressive, and that's how CG is actually used. Okay. Now, there are matrix-free methods for other problems, right? Actually, POC-Chambol, which probably many people here would know about, Beck to Boole, Stan Osher actually did a lot of the original, some early image stuff, right? Someone named Jacek Gonzio has done these kinds of things. And the idea is that they'll deliver modest accuracy in hundreds to thousands of iterations. That's kind of the idea. It's a different, you don't expect a matrix-free method to be as reliable as a matrix method. You don't. And you certainly don't expect it to give you high accuracy. right? But it turns out that's actually okay. Now, unfortunately, most of these things need a good preconditioner and tuning. They do need to be tuned, unfortunately. And in fact, that's something I'm going to come back to in a bit. Okay. Matrix-free cone solvers, because that is the intermediate form for convex optimization. We have compilers that will take a convex problem and compile it to this cone form. And so if you can have a good matrix-free cone solver, you glue these parts together and you've got a matrix-free CVX pi, which is coming, something like that. Okay. So this has actually been worked on. Gonzio has one. Stephen Diamond has been working on several things. A matrix-free SCS, that's one of the sort of standard solvers that comes in CVX pi or something like that. Another one is POGS, that's proximal operator graph splitting. Okay? And the details don't matter. The point is that there are actually some of these things that they exist. One thing that's very, very important, when you look at matrix-free algorithms and you go back to the literature goes into the 50s and the 60s, it goes way, way back. But you have to remember there's something very different about scientific computing and what we want. Scientific computing was, I want to solve this convection diffusion differential, PDE, okay? And so if you work on it for years and come up with a very clever preconditioner and tweak all the numbers right and you can solve it, you announce success. And someone says, wow, that's great. Then I solved this thing on this domain with so many mesh points and blah, blah, blah. Everybody following this, right? We don't want that. Well, we want a generic one. We want to get rid of the babysitting and we want to get rid of the tweaking and algorithm tweaking. That's what we want to get rid of. So what we want is a single method where you pass cone problems within reason from 100 different fields, vision, finance, control, any of these things. And what will come out, hopefully, not with total reliability, but what will come out will be something that's quite good and reasonably fast, a couple thousand iterations. Okay, that's what we want. We want generic. We're not interested in specific. All the research is on specific stuff, which is fine if what you do is a specific problem. Okay. Matrix-free CVX pi, again, this is a preliminary version done by Stephen. And what it does is it actually canonicalizes to matrix-free form. That requires a complete redo of everything, right? Because there are now no matrices. You're actually passing around abstract operators and you have to redo everything. And then, I like that. And then, that was like, those would be like, what? That's like 6 or 8 Stephen weeks. That's a lot of work, by the way, just in case anyone wanted to gauge that number. All right. And then you throw the result to a matrix-free solver. So that's what that is. And the goals, I should be very clear about the goals here. It's very important. So here's the goal. It's going to sound incredibly weird and modest, right? Because usually you go somewhere and someone says, oh, I solved this problem. How is it? You go, oh, I'm 5 times faster than state of the art. Oh, I solved the problem 3 times as big. Okay? Here's our goals. Ready? We would like to be within 10%. We'd like to be no more than 10x slower than a state of the art method. Okay? That sounds weird, right? You're not going to... But actually, let me explain why that's actually unbelievably impressive. Because it's going to work without algorithm tuning. And it's actually, to be blunt about this, it's kind of weird, but it's actually way more useful to have a method that is within 10x of state of the art and works out of the box in finance, statistics, machine learning, image processing, signal processing, networking, right? That actually is going to have a lot of use, a whole lot of use, right? Somebody in any one of those fields will fire it up and say, whoa, that's not a very, first of all, it's often the 3rd digit, and it took 5 times longer than my custom thing that, by the way, my grad student took 6 months to like tune and code. But that's just fine. We're happy with it. And I like to say that because people say things like, oh, will it be slower? And I go, absolutely, that's what we're shooting for. Yeah. I mean, we're not shooting for it. Okay, fine. But you know what I'm saying. We're intentionally lowering our I don't know what you want to call it, but it's, might as well be upfront about it, right? That's the key. Okay, so we'll look at an example. It's a non-negative deconvolution, right? So here's the problem. Now, if you represent this as a standard matrix method, it's kind of a disaster. I mean, here's what happens. C is converted. I mean, this is all handled, but it's converted to a topeless matrix because convolution is multiplication by a topeless matrix. Okay, fine. So by the way, all of this, your storage is instantly n squared. Okay? So by the way, n bigger than 100,000 is now totally out of the question. I mean, or stupid or something like that, but mostly out of the question. Okay. then, and the, the solve is order n cubed. Oh, now I should say the good news about the solve, if n is 1,000, this might not be so bad because it'll work perfectly. Always with total reliability. And it's going to get it out to 8 significant figures, right? So that's, and again, you know, you've already made the mistake of going into a field with a large number of variables. Too bad for you. But had you gone into a field with a smaller number of variables, then this would be fine. You'd be writing 8-line scripts or something. But maybe it wouldn't be as exciting, but okay, fine. Okay. Now, matrix-free method is you simply implement this as an FAO, right? So that's one of these computation graphs, a forward adjoint oracle. You make it an and then the memory is going to be order n, and the solve is going to be order n log n. Now, by the way, for something like this, many people have done custom things, and I think we come out at, I don't know, like maybe, in this case, like 80x slower. I don't know what it is, but it's fine. I mean, that can easily be improved. I guess there's a bunch of overhead and stuff. But, you know, the goal is not to make it the fastest there is. That's not the point. Okay, so this is what you would get. So this is n, so number of variables. That's like 10,000, 100,000, a million, 10 million. And then this would be with this is with an interior point solver. That's a tiny little solver, but, you know, runs on anything. And let's see, so this is, by the way, this scales, this is showing you the fit. And the fit says that empirically it's scaling exactly as you guessed from the theory, right? This would be the matrix-free SCS here, and this shows you that that's supposed to scale like n log n. Actually, I interpret n to the 1.1 as n log n. Seems fair, right? It's fine, right? And then this would be the same thing. This is running, by the way, single thread on a GPU, and then this is, this one is single thread on a CPU, and this is on a GPU. This one. And the only presumption about all this is that that's, I don't know, just overhead of getting stuff in and out or something. This is very preliminary, so these things are just going to get better. But the main point here is that the two things you see are exactly what's predicted, that that problem would have been absolutely impossible to go past 10,000 variables, but here you're comfortably going to, 100,000, million, and 10 million and things like that, right? So, oh, and I should add, there was exactly 0 tweaking of anything. Nothing, right? Absolutely no structure of the problem is used other than you take this problem and you, in a standard way, you compile that to a cone problem. Of course, that cone problem embeds an FAO that includes a convolution, but nevertheless, it's completely generic. Okay. And we'll just look at one more quick example, and then I'll wrap up. So this is a linear program where it's a different kind of structure. It's the kind of structure that comes up in control. And there you have a matrix. Capital X is your variable. And your constraint is actually just a bunch of linear inequalities. And they look like this. These would expand. That's, of course, that's a matrix. This is not a matrix inequality. It's an element-wise matrix inequality. And this is you multiply X on the left by A on the right by B. And then that matrix has to be less than or equal to, in element-wise, C. Okay? And so if you write this in the standard method, the memory is going to be insane. It's going to be order n squared. And the solve is going to be order n cubed. Right? The n squared is not particularly bad. That's fine. Well, I don't know. Okay, then the matrix-free method, if you do this, the memory is going to be order n, and the solve is going to be order n to the 1.5, right? And the details of this don't matter. It's just another problem for another. Oh, by the way, this is essentially the same code. It's identical. Nothing's tweaked, nothing's tuned. And you get something that looks like that. And so, once again, what you see is that ECOS is doing very, very well up to, somewhere up to here. And then, and so this is the world again, if you can, by the way, if you're just like a first-year grad student and this is your first time here, you could bail on vision and go back to a field with 10,000 variables. Okay, but anyway, I probably shouldn't have said that. Anyway, so this is the land where a lot of people work and play, is over here. But for bigger problems, this says we're actually solving quite big problems here, right? And it's completely generic, so there's no tuning, no nothing, right? So, okay. So I'll just summarize, and then we're gonna have time for questions. So the first thing is that convex problems they come up in a lot of applications. And you can solve them effectively. I mean, I should say a couple of things. I presume we'll get into this in the questions. No, most problems that you actually want to solve are not convex. My observation is that when you're trained in these methods, you can actually be unbelievably effective in practice, right? Because even things that sound very crude approximations actually usually end up really well. I'll say some more about that later. So you can solve small and medium-sized problems right now using, extremely conveniently and extremely reliably, right? If you go to bigger problems, then it's not fully there right now. It's partly there. It's not nonsense. There's a version of this that was actually produced, the results I was showing you before. But our goals are very, very modest, right? The goal is to make, in fact, here it is. The goal would be that people can do research in vision by typing in your objective and then calling the solve method. By the way, even if that's 10x slower than a good custom method, and it's going to be at least 10x, this actually makes a lot of sense for research because it means what you can do is you type in what you want, you try it, and if it's bad enough, you'd go drink an espresso. That's not a big deal. You come back, and by the way, if it doesn't look like what you want it to look like, then think of all the time you didn't waste by having your graduate student code it in C++. Okay, by the way, if you're a grad student, what I'm saying is very important to you. Okay, so that's the idea. Okay, so this is the whole idea. So, okay, I'll just finish up by saying, if you type anything related to any of these things into Google, you'll find everything you need. Everything's online, everything's on GitHub, there's tons of stuff there. I should also say there's a lot of people working on this, and so whatever you do, don't say something like, oh, with your methods or something like that. So maybe the CVX Pi, and don't even say it there because it's Stevens. So, okay, good. I'll quit here, and I'd be very happy to answer questions.
Stephen, thank you for this really nice presentation. Following Nesterov and others, there's a number of iterative solvers. They typically show that these algorithms have optimal convergence rates among all possible first-order methods. I think most of the latest iterative solvers have these properties.
Yeah.
How is that for the methods you presented here? Do they also have the same optimality guarantees in terms of convergence rates?
That's a great question. And so here's the answer. Ready? No, they don't. In fact, most of the methods we have the theoretical complexity that is the worst possible theoretical complexity for solving a convex problem. If you want theory, they do solve it. So there is a theory that says they'll solve it. It may take a couple of thousand years according to the theory, but they will solve it, right? So no, the methods we use actually don't have optimal order. Some that have optimal order do work better sometimes in practice, right? But it's a good question, and we don't. And I don't know if you've noticed, I'm not apologizing for it. But it's a great question. Oh, and I'll be very happy to use one, when we check it into these things and things run faster, I'll be delighted to use it. And then I will definitely say, plus, it's optimal order.
Drew?
Thank you for the talk. I actually have a comment and a question. So the comment is, you said many times if you're a grad student, X versus 10X is not a problem. I'd say when X is a week or if X is 2 weeks, which is often is for training large networks, deep networks, 10X is simply unusable.
Okay, sorry. Could you just stop for a minute? I wanted to time it. I just want to see how long it's going to take for that to come up. Good. Thank you. Keep going, please.
Well, you started it, so.
It's true. I started it. It's true. Fine.
So that comment aside,
that's totally cool. Yeah.
When you have to wait for an iteration, which is a month, that's just, nobody's going to use that.
Yeah.
But I certainly see the effort.
Yeah.
My question is, when you were making the connection to MatrixFree Methods, and you mentioned actually deep learning as well, I saw an immediate connection that I thought you would make, which is matrix multiplication from the right and the left. That's exactly the forward operation and the backward operation in a neural network. Like the backprop. Yep. And the duality between the copy and the accumulate operator is again backprop. Yep. And convolution would be again a linear operator, except you don't, in principle, you don't have to implement it with a matrix method. Except today's implementations do the exact opposite, where they will implement it with the matrix.
Yeah.
So are those things that you've thought about, and are there implementations for
Yeah,
that?
so can I rephrase it a bit?
Sure.
So yeah, I should say that the idea of a computation graph, and I mean, electrical engineers have known for like a gazillion years that if you make a node and it splits, that's a copy, and then when they turn them around and they come together, it's implicitly a sum. So that's been known like, 1945. If you talk to an electrical engineer, they would tell you that. So I think computation graphs are not new. This particular form of the Sylvester operator, it also computation graph is part of, if you look at what's backpropagation, I think it's called the chain rule in calculus, last time I checked, but I mean, maybe there's some subtlety I'm missing, but last time I checked it's chain rule, and I'm pretty sure that was pretty well known in 1750, but okay. I'm just saying, okay, so, and indeed, I mean, chain rule, the fact that you have a chain rule suggests that even all of calculus works this way. So yeah, these are themes, there's nothing novel in any of the idea of a computation graph and things like that. So, but it is cool to note that the same things show up. And I'll add something to your question. I was sort of hoping you were asked, like, well, how can you use these ideas for deep learning and stuff like that? I was going to wait for somebody to ask it, but I'll just ask it myself. Here's the question. I don't know. I have no idea. I can't think of any way. I mean, maybe, right? So we'll see. Oh, by the way, I do want to respond to part of your question, which was that you could make a grad student go out for a month and do this. There is actually a pretty big difference. I mean, I should say Jeff Hinton is a friend, so is Andrew Ng. We talk a lot. I actually think this stuff is fantastic. What's interesting, and certainly depending on what you're doing, absolutely, I would train a deep neural net. I'd go buy yourself a giant pile of GPUs and go do some. And this is if you have access to enough data. I would probably do that, right? Of course, that requires that you hire some of Jeff's students or Andrew Ng's students, and they're very expensive right now, just so you know. So, I mean, that's a downside, again, from a business point of view, right? By the way, that's a super duper upside for the rest of you, if you are one of those people. Nothing wrong with doing that. What I have noticed is, there's this method, so I don't have anything bad to say about that. What I have noticed is a lot of times people jump to that before they know basics. These are basics. In fact, here's what convex optimization is. It's shallow learning, right? It's just shallow. It's a one layer network. That's what it is. Okay, it's nothing else. And I'm not embarrassed. I'm not apologizing. It's shallow. So all of this is fine. I would be happier, just personally. I'm just saying I'd be happier if when I talk to someone and they say, "What'd you do?" "Oh, we used a deep neural net. Oh, net, and we trained it with 1 billion images and blah blah blah." And that's great. Good for you. If I'd say something like, "Did you try logistic regression and generate a few obvious features by hand?" Unfortunately, I'm sorry to report, this is not a careful example. That 85% of the time the answer is no, or even worse, what's that? So I'm just saying, okay? And I don't like that. I don't know. I would be happier if they said, "Oh yeah, we tried that. In fact, we tried your CVX Pi." And then they could say to me, I'd be happier if they said, "Not only was it super duper slow, but the results were crappy." That would make me happy.
Isn't that the same
Weirdly,
line of...
that sounded weird, but okay. Yeah.
Isn't that the same line of thinking that says we're happy if this becomes a technology and nobody understands what's in it?
Sure, that's fine. Well, so actually there is a big difference, though. And a big difference, I was having a conversation, before the talk. The big difference would be this. Let's be super practical. I run a company. We do something like we do fraud detection. I don't care what we do. It's a hedge fund. I don't care what it is, right? I'm not sure that I wouldn't prefer somebody doing this. Because they would say, "I wrote 12 lines of code, we're doing logistic regression, we did this, we generated some new novel features this way, and here it is." Then they get a little thing, and I'd say, "Oh, could you do better with a deep neural net?" And they said, "Oh yeah, we tried it, and yeah, it works better." I might actually go with this, the shallow method. And I'll tell you why. Because it's simple, it's actually simple, and it's maintainable. It's actually maintainable, because now when someone comes in and says, "Oh my God, we just got the best features in order to predict stock or whatever movements," you wouldn't believe it. I'd like to incorporate it in there or something like that. It's done. It's done immediately, right? If it stops working, for God's sakes, the entire thing is like 60 lines of code, right? we can figure it out and stuff like that. So I'm not sure. So I think there are some hidden costs to this. Having said that, I think it's just great. So, okay.
Any other questions? Raise your hand or wave so that we can see.
There's someone about 1 kilometer away back there.
It was 2 kilometers.
Okay, yeah, there. But you have fast runners.
Hi, Stephen. Thanks for your talk. I'm from NVIDIA, and I had a comment and a question. My comment was when you showed the graphs for the GPU, and it was flat in the beginning, it was probably because the GPU wasn't saturated with enough work. And you started seeing the scaling when it actually had enough work. And the other question I had was, have you thought about maybe porting it over to machines with multiple GPUs, the optimization solvers?
Those are both excellent questions. I want to clarify, the good news is that Stephen and I have the same first name, that your question really was going to Stephen, but I think he heard it as well. But I'll answer. So yes, you're absolutely right. This was like a first implementation, and it's almost certain that, you know, that's exactly it. We weren't giving it enough work or anything, something like that. That's fine. So on the first one. The second was the multiple GPU thing. Yes, there is at least one person trying to run these to multiple GPU things. But we actually really would like to even just optimize the single GPU implementation first. So, but yeah, those are great. This is, I guess, at Berkeley. I forget who it is. It works on roofline design, right? Where you make sure all the computation hardware is running absolutely at its limit. This was like, you know, I don't know, like the lawn design. We were so far from utilizing it. But your points are great, and you should talk to Stephen. Sorry. I mean, please do.
So let me ask one last question.
Sure.
So it was absolutely fantastic to see how in convex optimization you have a solid theory and you can apply to many problems in a unified fashion without having to tweak. And we profited in the computer vision community, and ADMM became very popular, let's say, up to 2012.
Yeah, okay. Okay.
But now the world is non-convex. And there is some practical results showing how non-convex, you know, instead of using the convex relaxation of the non-convex, directly solving the non-convex can be better in practice, or there are theoretical results, but now it's very non-unified, because for that specific problem, that is my theory, and that is the algorithm, and likewise. So what do you see, and do you see any hope of a unification as we move forward? And are there classes of non-convex for which what you presented today would eventually be possible to do the unification?
Well, I think, actually, that's a great point, and I agree with all of it, except I think what's undervalued is how far you can get with convex optimization. I mean, for example, I teach a class, and we pretend like everything's convex, right? But the truth is, what you really are doing is you're acquiring these skills. And then, I mean, there's convex optimization, the fancy stuff, and then there's what we call street fighting convex optimization. That's dirty. It's not just that there's no theory. It's like, you know nothing. But people trained in that actually are unbelievably effective, by the way, at non-convex problems. So on that question, like, you know, which is it, should you just do? The answer is I don't really know. Probably, I doubt it's the case that simply going back, reverting to gradient, which would be kind of hilarious, we all have to admit, right? Just saying, oh, screw it, throw it all out, let's just do gradient. I'm sure that I know for a fact, actually, that works really well in some problems, right? In others, it doesn't. I mean, at least in one instance that I know of, you use convex optimization to solve a horrible non-convex problem. You get close to the solution. In fact, the relaxation smooths things out. So you get close to the solution, and then you start some greedy method where you start tweaking variables and do nearest neighbor search. And I think for a lot of cases, I suspect something like that is going to work pretty well. So that would be my guess. But in other cases, it's not, in which case, fine. Let's all go back to gradient. It's 1730 again. Sorry. But we have way better computers than 1730.
Well, let's all thank Stephen for a fantastic talk.
Okay, thanks. Thank you. Thank you.